Well, we're at the last day. This is day 7 for Chapter 2. It's our last day for circular motion, and it's our second day for looking at orbits. And we're going to look at some of the work of an astronomer by the name of Johannes Kepler, and the work that he did showing us how planets actually orbit things like the sun, or how satellites go around the Earth. So these are called Kepler's 3 laws of planetary motion. And Kepler actually studied the path of Mars in order to notice how things were actually working, in order to get his math totally dialed in and checked. And by the time he was done, here are the 3 laws that he noticed. Very first thing is that planets don't have to go in a circle. So I lied to you in the last lesson when I said, oh yeah, look, circular orbits. Yeah, they don't have to be. They could be, but in general, they only have to be an ellipse. And the sun, the thing you're going around, is not actually in the center of the ellipse. It's actually at a very special place called the focus. So I'm going to put some pictures up here. You probably don't want to copy them too quickly until I say, yep, that's the one to copy, because I'm going to keep erasing it and then correcting it. So this is wrong, right? Don't copy this, right? This is the idea that, oh yeah, you should have circles there. Got the sun, got the Earth going around in a nice circle. That's what I told you last day. It's a bit of a lie, right? And the idea that it always has a constant speed, also a lie. Let's redo this. So we don't want to have a circle with the sun at the center. Instead, we want to stretch it out, because it could be stretched out. And the sun is not actually going to be in the center of this thing. It's actually going to be off to the side at these 2 special places, at one of these 2 special places called foci, right? Or focus for each individual one. And so you might find the sun over here. And now, when that planet goes around the sun, it turns out its speed is not going to be totally stable. Because as the planet goes on this trip like this, it's curling around the sun, but it's also going to be going away from the sun. And so the sun's going to be like grabbing on the rear bumper of this car and pulling back and slowing it down. And that's true until it gets all the way out to here. And now the sun is going to be grabbing on the front bumper, pulling it in and making it speed up. And so it actually ends up doing this sort of story. You're going to have the fastest speed when you're at that point of closest approach. And then it slows down while it goes away, because the sun not only is turning it, but also pulling back on it. Slowest speed is here when you're the farthest from the sun. And then it will speed back up on the way in. And so that's the first law. Okay, Kepler said, hey, be aware of the fact it doesn't have to be a circle. An ellipse will do just fine. And the sun's going to be off center, okay, over at this geometry place called a focus. The closest point, that's going to be when the force is the largest, because the R value is the tiniest, right? So you're going to have the minimum R, you'll have maximum force, you'll actually have maximum acceleration as well, right? Because forces create acceleration. And the reverse would be true at the farthest point, where you have the maximum R, you'd have the smallest force and the smallest acceleration. Okay, I'm going to scroll that up a little bit. Here comes the second law. The second law talks about just the speed and how it slows down when it's farther away. And Kepler noticed mathematically that if you were to imagine a string connecting the sun and the Earth, I know it'd probably burn up, right? But maybe some special string that doesn't burn. If you connected the Earth and the sun with a string, then that line, that string joining the planet and the sun, it actually draws out, it sweeps out equal areas in equal times. Okay, well that's an easy thing to say. What does it mean? It means this. I'm just going to shade that in a little bit there. And what you can see is I've kind of drawn in how that string would sweep out a little almost triangle shape of area when the planet moves here, or a little triangle over there that's got a smaller base but a much bigger height to it here. If those areas represented the same amount of time, like maybe 1 month for the orbit, remember it does go faster here, right? So that's why the base of the triangle is bigger. If you did go for the same amount of time, you would find that those 2 areas match. So one triangle is really short but wide, and the other one is very narrow but tall. And as long as you were to use the same amount of time to let that string draw the area out, you would find that it has the same amount of area. There's no real math that we're going to do with that. We're just going to say, yep, we get it. When the planet is close, it goes fast. And when the planet is far away, it goes slow, right? That's the key takeaway there. Well, gee, that's two of the three laws. Here's the third, and it sounds pretty mathematically technical. It says for any solar system, like ours, the square of a planet's period, t squared, is proportional to the cube of the orbit radius. Whoa, okay, well that sounds a bit intense. Let's tear this apart and put it in common language. The farther the planet is out, the longer it takes to go around. But not in a nice proportional way. It does it in a weird way where you have to think about the square of the period and the cube of the radius. So let's look at a couple of different planets here. Maybe one of them is, like, I don't know, the Earth, and the other one could be, I don't know, Neptune. And so they each have their own radius of orbit. Radius 1 looks smaller than radius 2. And that tells me that the time for the Earth to go round is going to be less than Neptune, but it does it in an interesting mathematical way. And here's how you can write down that proportionality in math. You could say, all right, the period squared for planet number 1 is equal to some constant multiplied by its radius cubed, and that constant would be the same as the constant you could use for planet number 2. So you could say, oh, that works for planet 2 as well. Planet 2's period squared is equal to the same constant times its radius cubed. So if we divide, we notice we always get the same constant, right? And that's going to be how we're going to kind of attack this problem. We'll say, all right, no matter what planet you look at, if you take its period and square it, divide by its orbit size cubed, you always get the same number. That's true for this blue planet, and it's true for this green one. Maybe true for the Earth, and true for Neptune, as long as they're both going around the same thing, both going around the same sun. So you could say, yep, not only is that a good constant for the blue Earth, but same constant you could use for green Neptune. Now, I usually tell students don't bother copying this, but we'll just take a look. I'm not going to stop you from copying it. Here's why it's true. There is only one force, just the force of gravity. So this is actually just a repeat of the last lesson. But if I'm going to do F net equals ma, and there's only the force of gravity, then that's all I can put in on the left, just the force of gravity. And since we're talking about the period of this orbit, I'm going to go with the period version for my acceleration. Played this game before, you guys have seen it. The little m's can go away, and then you can rearrange this until it looks like this form. So last lesson I was saying, yeah, we like to leave it in this weird form, t squared on top of r cubed. And here's why. All of the numbers over on this left-hand side are talking about the planet going around the sun. Those are planet-specific numbers. There's nothing about the sun there. And then everything over on the right-hand side is not talking about the planet. All right, there's one number in there talking about the sun, right, or the central body, if you wish. But you have planet numbers on one side and non-planet numbers on the other. So as long as multiple planets go around the same sun, the red circled number would be the same. That's your constant, right? That's going to be the same for every single planet. So how do we use that? Well, I want to show you two different ways as we finish up this chapter. Let's calculate how long the Earth's year is. I know, it's on the formula sheet, but we'll pretend it's been covered up with coffee, and we're going to try to recalculate the number. So I could go with what we did last day. This really is nothing new than last day, right? T squared on top of radius of the orbit cubed is equal to 4 pi squared on top of big G, always the same number, and big M. This is the mass of the sun, okay, the mass of the central body. If you're going to use this F net equals ma version, you must make sure you're using meters for the size of the orbit, kilograms for the mass of the central body, the sun, and you will get an answer in seconds for period. And it works great. You throw the numbers in, you take a square root, sure, there it is. That is how long the year is for the Earth. So that's one option for this Kepler's third law. You can say, yep, t squared on top of r cubed for one single planet equals this 4 pi squared on top of big G, big M number, talking about the sun. But that's not the only way you can use Kepler's third law. Here's another. Oh yeah, if you're curious, sure, that's around 365, 366 days. Here's another option. Let's compare one planet to another. As long as they're both going around the same sun, we should be okay here. So it says calculate the revolution period for Mars using the Earth's info that we already know, given one little clue. the size of Mars's radius, right, its orbital radius, is 2.28, 10 to the 8 kilometers. Okay, a little bit bothering that it's in kilometers, but it turns out it won't be. So what I'm going to do is I'm going to try this a little differently. Instead of going t squared on top of r cubed, like the last one here, and then the 4 pi squared big G big M, well, they both equal the same 4 pi squared on top of big G big M, both Earth and Mars. So let's just say those two fractions are equal. The Earth's fraction has to be the same as Mars's fraction, as long as we square the t and cube the r. So that's what I'm going to do. I'm going to put the Earth on one side, Mars on the other, and I can find one missing thing. Now I'm going to deliberately throw caution to the wind here, just to show you that I can. In the previous example, we said, no, you have to use meters and kilograms and seconds. Here, you don't, because it's proportions. So for the Earth, if I choose to, I could put in days for the time for the Earth to go around, and I could put in kilometers for the size of its orbit. That's fine as long as I respect the fact that it will be the same units over here. And that works nicely because they did give me 2.28, 10 to the 8 kilometers for Mars. When I solve this with some cross multiplying, I'm going to get a value for the period for Mars, and apparently it will be in days because that's how I jumped into this problem. So there I am cross multiplying. I can find the square root of the t, take a square root, I'm done. So the time for Mars to go around the Sun is 684 days. So I'm just going to summarize that really, really quickly, just with one last page here, because we've done two different kinds of calculations for this third law. If you're going to compare satellite to satellite, like we just did, okay, if that's what you want to do, any units are fine, but you have to be consistent. If you're going to go satellite to central body, that's when you're doing the whole t squared on top of r cubed is equal to 4 pi squared all over big G big M, then you must use meters, kilograms, and seconds. There's no way around that. And that totally wraps up this chapter. And we're all finished.